All right, now in this video, we are going to do the 3.1.5 practice assignment, which is non-graded, which is why I will do it completely here for you. And if you have questions afterwards, you can let me know. So in this one, we are going to be doing hypothesis testing, which is also called significance testing with the t-distribution. So when we've done hypothesis testing and significance testing before, we have only done one type of test, and that was called a z-test. But as you know already, now in 3.1, since we don't know the population standard deviation, we're going to be using t-distributions instead of z-distributions. So let's see how that changes things. So on this worksheet, we have two problems to work with, number 1 and number 2. So starting with number 1, after a long road trip during summer break, a college student wants to estimate how long she drove between rest stops. She takes a random sample of 15 stops, so n equals 15, and records this data in hours. All right, I'll come back to that data. So the first question is, what are her null and alternative hypotheses if she claims that she drove longer than 2.25 hours in between stops? All right, so our claim is based on this value right here. That means our H sub naught is going to be that the mean value is equal to 2.25. Okay, our H sub naught is always that our mean value is equal to a certain number, and that's like our base number. Then our alternative hypothesis will be what she's claiming. So she is claiming that she drove longer than 2.25 hours. So our alternative hypothesis will be that mu is greater than 2.25. So this is a one-sided hypothesis test. It's strictly greater than. I could draw my t-distribution, assume that maybe 2.25 is somewhere around here, and we're going to be looking for this area, which is our p-value, and hope that it is less than our alpha or our significance level. Okay, so I do want to write this in context as we like to do when we're doing a significance test or a hypothesis test. Step 1 is that we not just say these hypotheses, but that we say them in context of the problem. So if I was doing a free response option here, and I was just doing a significance test in general, I would write those down first of all like that. And then I would have to interpret them and talk about what that means in context of the problem. So H sub naught, our null hypothesis, is that she drove 2.25 hours, equal to 2.25 hours in between stops. The alternative is that she drove more than that. So this is how your step 1, stating your null hypothesis, should look in a free response. You don't just list H naught and HA and then continue. If you're doing a any free response portion of a test, you always want to write down the interpretation of the numbers that you wrote. Okay, part B. What test should you use? That's always our second part of our hypothesis test. What test should she use? How will she test work? How will the test work? What are the conditions necessary to use a test? How does the situation meet the conditions necessary for using a test? All right, so as you might already expect, in the last unit, we did z-tests. In this unit, we're going to do t-tests. So that was part A. Part B, we're going to do a t-test. We will perform a t-test with significance level alpha equals, and let's make sure they don't tell us which alpha to use. Oh, it does say back down here at the bottom that we should be using alpha as 0.05. Good thing I checked. So we're going to use alpha as 0.05. We always like to state that in our second step. You don't want to say your alpha at the end of your significance test because then you can get accused of kind of rigging your test. Okay, we want to decide how accurate we want our answer to be before we start doing the test. Okay, and then are the conditions met? Well, what are the conditions for doing a t-test? What are the conditions for using a t-distribution? Remember, they had to be not necessarily normal, but we either had to have a large sample size with some skewness maybe, or a small sample size with no outliers or extreme skewness. Okay, our sample size here is 15. That's not greater than 30, so this is a small sample size. So I'm going to need to pause right here and look at this actual distribution and make sure that there's no outliers or extreme skewness. So we're going to grab our calculator to do that real quick. And I'm going to put all this data that they've given us into my lists so I can create a stat plot because I don't really want to do that by hand right now. So I'll go stat, edit, clear out that data and put in this one. Pause it so I can do some magic. All right, voila, magic. All of my data is in there. So now I'll go ahead and create a stat plot. Second y equals, turn on that first plot. And for checking for outliers as well as skewness, the modified box plot is best. So I'll choose a modified box plot. My data is in list 1, so I'll change it to list 1 by hitting second 1. And if I want to change my color, I can do that here. I'll just make it green. And then when I hit the graph button, it's probably going to be in a weird spot. I can zoom. Oops, I got a line in there too. So I need to get rid of that line real quick. I'll go y equals and clear out that random line in there. And while I'm at that, I'll also adjust the zoom to the stat-friendly zoom, zoom 9, so I can see my box plot. And what we're looking for here is we don't want outliers. Outliers would show up as dots. I don't see any dots. And we don't want skewness, extreme skewness. A little bit of skewness is fine in a t-distribution because our t-distribution is robust. But we want to make sure there's no extreme skewness, which means we need to make sure that these whiskers are not too long. And I would say, in comparison to each other, one is not ridiculously longer than the other one. There's a slight skewness to the right here, but not enough to worry about in a t-distribution. So our conditions are met because we're going to say based on the modified box plot, which I'll draw a picture of. You cannot refer to a plot without at least a sketch of it drawn. We don't need the numbers here. We just need the shape. So based on the modified box plot, there appear to be no outliers or extreme skewness. So we can go ahead and do our t-test. Okay, so that's part B. Now we're on to part C, which is calculate your test statistic. Show your work, including the formulas that you used. All right, so I guess I will start by running the formula that we use to calculate a t-statistic, which is almost identical to the formula we use to calculate a z-statistic. We're just going to use s instead of sigma. So our t-statistic is equal to x bar minus mu over s divided by the square root of our sample size. Okay, so that was part of the requirements. I had to actually write the formula in there. Now we're going to plug our things in. Okay, so I have mu. Mu is my 2.25. I have n. N is 15. I need to pause here now, though, and get my x bar and my s. And since I have a calculator handy, and I already have my data put into my lists, I'm going to get my x bar and my s by doing a quick calculation of one var stats. And there it is. X bar is about 2.52. And S sub x is about 0.73. Okay, I'm going to leave probably 4 decimal places there, though. So x bar is 2.5233. And S sub x is 0.7272. We already had n and mu. I'll just write them again just because. So let's plug them in and see what we get. So our t statistic is going to be x bar 2.5233 minus mu 2.25 divided by s 0.7272 over root n, which was 15. Make sure you can see what I'm doing. Nope, gotta move you down a little bit. There you go. All right, so now I'll go ahead and do some quick calculations there. So in my numerator, I have 2.5233 minus 2.25. And in my denominator, I have 0.7272 divided by the square root of 15. Oops, which is 0.18776. And then I need to divide top by bottom. 0.2733 divided by that denominator gives us our t statistic, 1.4556. All right, there we go. So that's part C, calculated my t statistic. Does not say to calculate my p-value yet, looking back at my directions. We know usually in our hypothesis test, after we calculate our t-statistic, we would also calculate our p-value so that we can compare it to our alpha. But looking at my directions, it says calculate your t-statistic, show your work, include the formulas you used. We did all of that. And then it says, what's your conclusion at alpha? Okay, there's nothing in here that says to calculate your p-value, but you can't get a conclusion without your p-value. So let's go ahead and calculate a p-value really quick so that we can compare it to alpha in part D. That really should be part of part C. So our p-value, again, we're trying to show that mu is greater than this 2.25. So now that it's a t-value, I am going to try to show that t is greater than this number, 1.4556. Okay, so our p-value is a probability that that is true. And we can calculate that probability using TCDF on our calculator. So stat, calculate, oops, not that one, distributions, that's what I want. TCDF, option 5, or no, option 6. Lower bound, let's see, we want greater than 1.4556, so that is my lower bound. My upper bound then would be infinity, so I'll leave it like that. And my degrees of freedom, well, my sample size was 15, so my degrees of freedom is 14. So that is about 0.0838. All right, so that is my p-value. And now I can compare that to alpha. Remember, if our p-value is less than alpha, then we reject our h sub naught. If our p-value is greater than alpha, then we fail to reject h sub naught. Those are our only two possible conclusions. Well, let's see, our p-value is 0.08, which is greater than our alpha, 0.05. So our p is greater than alpha. That means we failed to reject our h naught, which means we cannot say that this is necessarily not true, which means we cannot say that this is necessarily true. So our conclusion for part D, I would put, since our p-value and hold on one second. There, now you can see what I'm doing. Since our p-value is more than our significance level, we fail to reject h sub naught. Okay, so that's kind of our generic answer. Now we need to say that in context of the problem. What does that mean? That means that this is the hypothesis we're going to go with. we cannot support this hypothesis. So we say it is not likely, not saying it's impossible, but it's not likely that she drove more than 2.25 hours between stops. And that's it. That's the end of that one. Okay, number 2, we're going to do the same thing, but this time it looks like we're going to do a little bit different. So it says, imagine a scenario exactly the same as in question 1, except, oh, you can't see what I'm doing. Of course, you should have the paper. Yeah, there it is. Okay, imagine a scenario exactly the same as in question 1, except that this time the college student isn't sure whether the mean travel time was less than or greater than 2.25 hours. Okay, so what we're saying here is now H sub naught is still 2.25. Oops. But our H sub A is now two-sided, not equal to 2.25. Okay, so it can be greater than or less than. So it says, recall that she wants to use hypothesis test to estimate how long she drove between rest stops. We're going to state our null and alternative hypothesis for the test. There they are. Part B says, describe the type 1 and type 2 errors associated with this hypothesis test. Grab that for you. There they are. Remember our type 1 and type 2 errors here? So a type 1 error would be that we reject the null hypothesis when the null hypothesis is actually true. So if we reject this when it's true, then we would say that she did not drive 2.25 hours when she did. Okay, doesn't say to talk about the implications of that, just to state what type of error, what that error would look like. Okay, and then type 2 error, again, right here, type 2 error is that we fail to reject the null hypothesis when the null hypothesis is false. So that would mean we would say this is true, but it's actually false. So we would decide, she did drive 2.25 hours between stops when she did not. Okay, so I don't really know what the implications of her driving is, but those are what the two types are. All right, next part. Set aside. It says compute the 95% confidence interval for this test. Okay, so we're not doing a hypothesis test outright here. We're going to do a 95% confidence level instead. All right, they have the same result. We can totally do a hypothesis test here, but they're asking us to do a 95% confidence interval. Remember, that's going to give us the same conclusion as if we were to do a hypothesis test at a 0.05 level. All right, so let's see. 95% confidence interval for this test. So that's going to be, again, we're on part C. It's going to be X bar plus or minus T star times S over root N. So that we know all the data that we need to collect. Okay, I already have X bar and S from my last problem. I'll go ahead and pull those out again. Okay, X bar was 2.5233. S sub X was 0.7272. And so the last thing that we need this T star here, which I'll just use my table for. T stars are pretty quick to find with your T table. There it is. So we need a T star for a 95% confidence level with, we had 15 pieces in our random sample. So a degrees of freedom would be 14, right? N was 15, so degrees of freedom is 14. All right, so let's see, degrees of freedom 14, confidence interval is 95%. Just shows on the bottom here, 95% is associated with a tail probability of 0.025. So we're at 2.145 here. So our T star is 2.145. Go. And there we go. That's all that I need to calculate my confidence interval. So let's do it. So X bar plus N minus T star times S over the square root of N. So I can stick that in my calculator real quick. Order of operations, since I got to start here. 0.7272 divided by the square root of 15 times our T star gives us that margin of error. So I'll write that in. So we have X bar, our estimate, plus and minus our margin of error, 0.4027. So subtract to get my lower bound, 2.5233 minus lower bound is 2.1206, upper bound 2.5233 plus upper bound is 2.926. So again, that means we are 95% confident that the true mean is between these two numbers. Okay. So we computed that. So D, what is our conclusion? At alpha is 0.05. Okay, well, let's see. This is a 95% confidence interval. Is 2.25 within that? Yes, it is. So our conclusion, H sub naught mu equals 2.25 is within our 95% confidence interval, which means, again, we fail to reject the null hypothesis. Okay, we can't say this is not true because it looks like we are 95% confident that it could be true. So we have the same conclusion as before, even with a two-sided test. All right, next it says, what is the probability of making a type 1 error in this test? Okay, coming back to this, we talked about this before. Here, the probability of making a type 1 error is alpha. Okay, we chose alpha was 0.05. In a 95% confidence interval, alpha is 0.05. They're unanimous. So part E, the probability of making a type 1 error is equal to alpha, which is equal to 0.05. Okay, so even though I didn't do an actual significance test here with alpha with a significance level, a 95% confidence interval is the same thing as a hypothesis test with a significance level of 0.05. Okay, again, if I did a 99% confidence interval, then that would be the same as having a significance level of 0.01. Okay, part F, what is the probability of making a type 2 error? And what is the power of the test if the true mean is 2.5? Okay, so for that one again, back here, this is again 2.4 that I'm looking at. The probability of making a type 2 error is beta, which is 1 minus the power. And the power of the test is the probability against making a type 2 error. So let's see. So we had here our instructions for finding the power of a test. So to do that, we have to find the rejection region and then calculate the probability that we end up in that rejection region. Okay, so give me a second. Okay, sorry. So back here, so remember the rejection region is the region outside of our confidence interval. Okay, so we need to find the probability that our t-value is outside of our confidence interval. That will be the power of the test, and the complement of that is the probability of making a type 2 error. Okay, so for part F, okay, I'll write some notes here for you. The power of the test is equal to the probability that t is outside our confidence interval. We call that region outside our confidence interval the rejection region. So we have our confidence interval up here still. So we are going to calculate the probability that t is either less than 2.1206 or that t is greater than 2.926. Given that the true mean they said was 2.5. That's important. We know the true mean here is 2.5. All right. Okay, so we do know in a confidence interval that these two sides are going to be the same. So I could just find one and then multiply by 2 to get the other. Okay, so give me 1 second. All right, I realized what I was doing wrong here. So we can't calculate probability like this, but we can calculate the probability that it is within this confidence interval, and then this will be the complement of that. So backing up here, I'm going to do 1 minus the probability that t is between those two numbers, 2.1206, 2.926. Okay. So when I do that on my calculator, I'll show you. We'll use TCDF to get the probability between two t values, right? So I go second vars to get to my distribution menu, go down to option 6, put in 2.1206 for my lower bound, 2.926 for my upper bound, degrees of freedom, and minus 1 is 14. And we get the probability that it is within that confidence interval is 0.0206. So we have 1 minus 0.0206. So I do that, 1 minus that. And I get that the power of our test is equal to 0.979. Pretty powerful test. And that also means the probability of getting a type 2 error, or beta, is equal to that original before we subtracted 1.0206. So there we go. We have the probability of a type 1 error, alpha, the probability of a type 2 error, which is slightly less, which is what we want. Oops, there it is. And our power of our test, which is very high. So that's great. Perfect.